Now, a moment ago, we found an algebraic equation. This algebraic equation could be simply written as ax equals x. And our A is this matrix we found from the backlinks, or say we found from the directional graph. When you say, hey, this looks like familiar, of course you know it. What's the definition? And somebody already told me, oh, this is an eigenvalue problem. And by definition, what it means eigenvalue? If you can write ax equal a constant times x, in other words, if you look at the transformation stay in the same direction of the original vector, you got an eigenvalue problem. In our case, we simply find this lambda equal 1 here. So the problem we found a moment ago for these 4 pages, and it's really an eigenvalue problem for the eigenvalue 1. And this x, by our definition, is called eigenvectors. And finally now you connect it to the title called the $25 billion eigenvalue problem. Well, that's an easy equation you can solve. And first, we don't want the 0, 0, 0, 0 solution. That's no use, because I really wanted the rank distinguish the relative importance of these 4 pages. And you can see the determinant of A, of course, equals 0. And you also could find the rank of A in this case is going to be 3. And then you have one freedom. In one freedom, you can find the vector, and a quick solution, you can find this vector. One possible solution, let me zoom a little bit, is 12, 4, 9, and what is the other one? Maybe 31, 21, 6. Well, that's also one solution. You can multiply anything, but in order to make it unique, you can use a unity vector. So you remember we talked about the eigenspace V of A. This eigenspace is one-dimensional because you have one freedom. Remember, the freedom equals the total number of variable, which is 4, minus the rank of the matrix 3, and then you have one freedom, means you get infinite many solutions, but all the solutions must stay in the straight line, in a straight line. If you have one straight line goes this way, I want you to make it positive, go one direction, and I want to make it 1. You only have one choice. So your choice is this vector. I missed the 1, x4. We divide by 31. By the way, total is 31. And then we got 0.194. And then we got this solution. Let me see. The solution is the first page, the most important, 0.387, come to the third, that's 0.29490, and then it's the fourth page. The last one, of course, is the second page. So that rank is a little bit of surprise. If we just count the backlinks, if you still remember, the third page have 3 backlinks ranked number 1. 3 backlinks. And the first and the fourth tied of number 2, they all got 2 backlinks. And the second have only 1 link is the last. But now the rank is, the first is the first page. That's number 1. And the number 2 is the third page. And the number 3 is the second page, the fourth page. And the last is number 2. So the rank is 1, page 1 to page 3, and page 4, page 2. So according to this calculation, Google will rank, put the first page first, the third page second, the fourth page third, and the last for the second page. That's what makes a difference. So you say, is that a real surprise? Well, if you understand that this voting system, you're not going to be surprised. Because the third page give all 100% vote to the first page. So the first page got all the score of the third page. Just like if I'm lucky, Yahoo give only a single link to my website, then my website will be more famous than Yahoo because all the weight come to me. So of course, that's impossible. So we understand why. It is not quite a real surprise, I explained, because the third page got all its vote, 100% give to the first page. So the first page now is ranking number 1. 1 is simply because the page 3 give all to the first page. Well, so after 3 different options, we finally seems to find a solution to the problem. Well, our example is very simple. Let's look at another example. In this example, again, only 5 pages. You know what make a best mathematician? The best mathematician or physicist, they can give an example as simple as possible. If they can make it a 5-pager, they don't give any 1 more page to help people understand the idea. So in this example, we got a dangling node. What it means dangling? Nobody connect to the 5th page. That there's no entries for that page. Nobody linked to this 5th page. Can you see that? Okay, that's called the dangling node. And also got the disconnected subweb. And these 2 subnets are not connected to each other. Well, that's a little problem. Let's see where's the problem. We do the same way. Let's check the first page. You get 1 connection from the second page. That's what the first page got. The second page got 1 backlink from the first page. That's what this gave. And the third page, we got 2 backlink from the 4th and the 5th. 100% from the 5th. And half from the 5th. You see, the 4th give all to the number 3, and the number 5 give half to the number 3. And so is the number 4. Got 100% of number 3, got half from the number 5. What about the number 5? We call it here dangling node. Well, this dangling node have nobody give any vote to it. So got all the zeros. So we got all those zeros. That will bring the trouble. I'm going to show you the trouble in a minute. But first, let's formula define what we call it stochastic matrix. You know, stochastic means probability. In that matrix, if you look at each column, it's 1. 1 in probability, of course, means 100%. In our previous discussion, we know that's just 1 vote for everybody. And if you vote for 3 people, each of these 3 got 1/3 of your vote. So that's why each column going to be at 1, because this is how we modeled this problem. And a stochastic matrix have a few requirements. First, each column is going to be added to 1. Second, no turn negative. They all must be positive. You don't have a negative probability anyway. So we understand this concept. And then next, I want to show you doesn't matter what kind of structure graph you have for your internet. You always has the 1 as your eigenvalue. How do we prove this? It's pretty simple. I just show you we can always find a eigenvector like this 1, 1, 1, 1, 1. Everything's 1 to the transpose of the A. And if you remember the A, each column add to 1. When I turn the column to rows, this means we transpose, means change the column to row. So each row will add to 1, right? Because each column add to 1. Let me look one more time. See, each column add to 1. If you change the column to row, each row is going to add to 1. So once you, each row, now this is the row for the A transpose. And if you let this multiply this vector 1, 1, 1, 1, 1, of course, you're going to get 0, 1. And you get 1, 1, 1, 1, 1. Let me see. And the first, the determinant is going to be the same. If you are transpose, that's a proposition of a determinant. You change row to column, the determinant does not change. And then, if you multiply the E to the transpose, you get exactly the 1, 1, 1, 1, 1. Let me just check this for you. Now, the first row times this. Now, this is the first row we transposed. And what you get is 0, 1, 1 times 1, you get 1. The rest are all 0. And now, the second row times this column, you get this. The first times this is going to be 1 again. And then, the third column row times this, you get 1 again. Or when you add all together, of course, you get again 1, 1, 1, 1, 1. What does that mean? That means A in transpose times E equals E itself. That's the definition of eigenvalue. The lambda equal 1 is the eigenvalue of A prime. So it's also the eigenvalue of A because the determinant is the same. So again, if you have any structure, if it's a stochastic matrix, we always get the 1 as an eigenvalue.